Hello, everyone, and welcome to Implicit Differentiation. Sometimes when you're studying two quantities, x and y, the only way you can link them is through an equation where that equation is such that it is algebraically impossible to isolate y as a function of x. But if we look at the resulting curve in the Cartesian plane, which is then not, of course, the curve of the graph of a function, but if that curve is such that for almost every point, the curve is locally differentiable, then it is possible to get an equation for the derivative. And typically that equation will also be an equation that will depend on x and y. So let's just look at an example visually. For example, if you look at the equation 25x squared minus 25y squared equal to 2x4 plus 4x squared y squared plus 2y4, the resulting curve in the Cartesian plane is this nice infinity symbol. But here, if you look at the resulting curve, that curve is not the curve for the graph of a function. If you do the vertical line test, there's a lot of x's that gives you more than y value. For example, at 3, you can see the y is either 1 or minus 1. So this curve is not the curve of a graph, of a function. And of course, algebraically, what does that mean? So this means simply that algebraically, you cannot isolate y as a function of x. But what is very interesting with that curve is that for almost every point on that curve, locally, it looks like a function. What do I mean by this? Well, for example, let's take the point 3, 1. And let's look at what's going on around that point. So just on a little chunk around that point. So for example, here, I will highlight this in orange. Boom. Okay, so here, starting at 3, 1, just looking at the surroundings. So if you just look at that portion of the graph, so here, just around it, let's just highlight that zone with a circle. So poof. So inside that little orange circle here, so just around there, we can see that that portion of the curve really looks like a function. So this part looks like a function. We don't know what this function is explicitly, but this is why this is called implicit differentiation. Haha. And what's really interesting to notice here is that at that point, 3, 1, for that portion, the intuitive idea of drawing a tangent line works. So if I do this in red here, poof, so you can see here the curve at 3, 1 is such that if you draw a tangent line, if you try to draw a tangent line, it works. And the goal, of course, is to find either the slope of that line or the equation of the tangent line there. So this is something we can do. But of course, if we start with an equation that depends on x and y, typically the derivative is also going to be an equation that will also depend on x and y. And this is what we're going to do in this chapter, just learn how to deal with equations where we have x and y in it. But really, there's no new rules of differentiation. We're just going to use the fact that we know how to use chain rule to compute derivatives. And the chain rule idea will be the core idea to get the derivative for an equation of two variables. Of course, not everywhere on that curve, the tangent line will exist. For example, on that curve, if you look at the origin, so the origin here, poof, if you look at the origin, because you have an intersection, if you try to take just a little chunk, a little neighborhood around that point, there's no way you can create the graph of a function. So you cannot compute the derivative of any intersection. You could think of an intersection as a combination of two corners kissing each other. So just like regular graphs for functions, every time you see a corner, there's no derivative. So if you see any corners or intersection on a curve, you cannot compute the derivative at that point. Again, you're just like with regular functions, graphs of function, if you see any point where the tangent is a vertical line, so here at the extremities of this infinity symbol, we have 2 points here where we have no derivative dy dx because we have vertical tangents. So here in red, just to put this a bit clearer, so any point in red here, the reason why there's no derivative is because we have corners. And then in magenta, the reason why there's no derivatives, no dy dx, it's because we have vertical tangents. And of course, if we had any points where the curve would break off, like kind of being like discontinuous, we would not have any derivative. So it's just like before. So here the idea is that if on a point, like the point 3,1, you can find like a neighborhood such that if you just take a little chunk around that point and that little chunk is the graph of a function, then we can compute dy dx. If you can't do it, so for corners, intersections, vertical tangents, or where it's not continuous, then you cannot compute dy dx. So I'm expecting you to be able to recognize visually where there's no derivatives or where there is a derivative. So here's the method in 4 steps of how to compute the derivative dy dx on a point, on a curve, where there is a derivative. So the first thing you do with your equation, the equation has 2 sides, the left side and the right side. You need to differentiate on both sides at the same time. So you have a big equation that involves x and y, left and right. You differentiate left and right. So then the second step is just to use the regular rules of differentiation. If you need basic stuff, product, quotient, or chain, you just do everything as usual. You don't really care initially if there's x and y's. You just do your rules, but there's some variables y involved. So how do you deal with differentiating a term that depends on y? So the third step is the crucial one. So here, the third step says that if you are computing the derivative of a term that depends on y, because y is a formula that depends on x that we don't know explicitly, you still have to use a chain rule to compute its derivative. So what do I mean by this? So for example, let's just do like a small intuitive example on the side to help us illustrate how to differentiate a term that depends on y only. So to help us build the intuition behind how to handle a term that depends on y only, let's just do like a simple example, what I call like an intuitive example. So suppose we want to compute, let's say, the derivative with respect to x of y5. So because it's y initially, you say, well, I don't know. Okay, I don't know what's the derivative of y5. I only know how to differentiate with respect to x here, something that depends on x. So here the idea, the trick is to say, well, let's replace y by some equation. And let's see what we would do in that case. For example, let's compute, let's say, the derivative of y, but now y will be specific. Let's say it's sine of x minus 2x. It does not really matter what you choose. For y here, we're just trying to build the intuition. So we have some shit, okay, to the power 5. Choose your own shit. So of course, if you're trying to compute that derivative, what you're going to do, you're going to use a little chain rule. So you have sine of x of 2x. So we have something to the power 5. So you're going to use a chain rule now, and you're going to get what? Well, you're going to get 5 times that shit untouched. The new power will be 4, and then you're going to multiply afterwards by the inner derivative. So the derivative of the inside, derivative of sine is cos, and the derivative of minus 2x is just minus 2. So why am I using this example? So now we can kind of see, like, if you call the inside of the power 5, if you call it y, you can see that what we got is 5 times y4, but then what we multiplied after by, it's not y again, it's the derivative of y with respect to x, or dy dx. So therefore, if you are trying this in general, if you are doing this in general, if you're going back to let's differentiate something to the power 5, you're going to get 5 times that something to the power 4 times the inner derivative. And here the inner derivative, we don't know it explicitly, but it's fine because anyways, This is what we're looking for. So the derivative of the inside is dy dx. So simply put, every time you have to differentiate something that depends on y, you just use the regular rules that you know, but make sure that you remember that inside the y there's an inner derivative that you don't know explicitly, but this is why this is called implicit differentiation. So you need to multiply every time by dy over dx for any terms that depends on y only. So you start with an equation of two variables with two sides, a left and a right side. You differentiate on both sides. You just use the regular rules of differentiation with a twist. Every time you differentiate something that only depends on y, you have to use regular rules, but you need to multiply by the inner derivative, the dy dx, and you need these dy dx because this is what you're looking for. And then once you have your equation differentiated correctly with the correct rules, plus this twist of multiplying by dy dx any terms that depends on y only, then you're just done. You're almost done. You just have to do some algebra, bring every terms that contains a dy dx on one side. Typically I choose the left, but it really doesn't matter. All the other terms will go to the other side. Typically I choose the right side. Then you can factor by dy dx and divide. So the idea is just to use regular tricks from algebra to isolate your y prime or your dy dx, and then you get a formula for the derivative of your curve, and that formula typically will be a formula that will depend on x and y. And then if you need to compute slopes or equation of tangent line, then you just use the ideas from standard differentiation. So let's go back to the infinity symbol and compute the implicit derivative for that curve. And in particular, let's compute the slope of the tangent line of that curve at 3, 1. And let's construct the equation of the tangent line at that point. So let's compute the implicit derivative of our infinity symbol. So we start with an equation. Poof. Okay, so 25x squared minus 25y squared is equal to 2x4 plus 4x squared y squared plus 2y4. So we have an equation of two variables. So what we're going to do here is we're going to compute the derivative on both sides. So the first step is to simply write that, okay, let's differentiate on both sides. Poof. So just by adding up the d over dx symbol on both sides, it shows that you understand that you have an equation of two variables with two sides, and you differentiate on both sides. We're going to differentiate on both sides. So the next line is the most important line of the computation. That line shows that you understand what implicit differentiation is all about. Once you have the next line, everything else is purely algebra. Of course, it might still take time to isolate the dy dx, but it's purely algebra. So the next line, very, very important, like boom. Okay, so you differentiate on both sides. This is what you're going to get. So I'm going to go term by term to explain what's going on here. So for 25x squared, so a term that depends on x only, you just do your regular stuff. The derivative of 25x squared is 50x. Minus 25y squared. Now we have a term that depends on y. So what you do, you just treat it as if it was a regular variable. So the derivative of 25y squared will be starting with minus 50y, but because we're dealing with the y variable, you need to multiply afterwards by dy dx. Remember, it's like we have some stuff squared, so you get 2y times the derivative of that stuff. So that's for the left side. Now for the right side, the derivative of 2x4, regular term, so you just get 8x cubed. But now for 4x squared y squared, now we have the product of two things. 4x squared is multiplying y squared, so I'm going to use product rule. So the derivative of 4x squared is 8x, so the next term is going to be 8x times y squared. I'm really using the uv notation, so u prime is going to be 8x, v is just y squared, plus 4x squared, not changing, and now the derivative of y squared is going to be 2y times dy dx. So every time you differentiate a term that depends on y, you need to multiply by dy dx. And then the last term, purely depends on y. So you're just going to get 8y cubed. So you just do your regular differentiation stuff. But because this term depends on y only, you get dy dx. And that line is the most important line. Once you have that line, things will get easier afterwards. So the only thing you have to do is find a formula for dy dx, but that part is purely algebra. So from that line, I identify all the terms with dy dx, and I bring all those terms on one side and then all the other terms on the other side. Here, because two of the three terms containing dy dx are on the right side, I'm going to bring all the terms involving a dy dx on the right side, and everything else will go to the left. So if I just move things around, I'm going to get the following equation. So poof. So the next equation that I get, so on the left, so 50x stays there, but then I need to bring the 8x cube on the left side as minus 8x cube. And also I need to bring 8xy squared on the left as minus 8xy squared. And then on the right, so the minus 50y dy dx will go on the right as plus 50y dy dx, together with the 8x squared y dy dx and the 8y cube dy dx. So you can see now every single term on the right contains a dy dx. And the reason why you do this is now you can actually factor. They all have that common dy dx factor, so you can factor by dy dx. So if you factor by dy dx, you're going to get, well, on the right, nothing changes. Sorry, on the left, nothing changes. On the right, now I have dy dx, which multiplies 8x squared y plus 8y cubed, 50y. And now that you factored by dy dx, you can just take the equation with the dy dx and bring it to the other side at the denominator. So you're dividing both sides by that equation. So this will give you a final formula for dy dx. So here we go. Boom. So that's the answer if we're asking you to simply compute the derivative of that equation. The answer, y prime or dy dx, is 50x minus 8x cubed minus 8y squared over 8x squared y plus 8y cubed plus 50y. So that's the derivative. So that's the hardest part of the question. Now, if we want to construct the equation of the tangent line, it's purely done by evaluation of that expression that depends on x and y now. And then if you need to find the equation of the form mx plus b, knowing that it passes through a specific point, you can figure out the b, just like a regular question where you need to find the equation of a tangent line. So if you want the slope, you just take your derivative and you're going to replace every single x by 3 and every single y by 1, so that process of evaluating your function where all the x's are replaced by 3 and the y by 1. The notation for it is this big vertical line. So dy dx at, so slash vertical line 3, 1 just means we're going to evaluate this expression at 3, 1. So here the only thing you have to do is replace every single x in your equation by 3 and every single y by 1. If you do that, so if you plug x by 3 and y by 1, you can double check that the m is going to simplify to minus 9 over 3. So that's for the slope. So if we're only asking you for the slope, that would be the answer, or the value of dy dx at 3, 1. If we want the actual equation, then at this point, what do we know? We know that L of x is a linear equation of the form minus 9 over 13 plus b, and we know it passes through 3, 1. So now you just have to replace the x by 3 and the y by 1 to figure out what is the b value. So if you plug y equal 1 and x equal 3, boom. So you're going to get that 1 is equal to minus 9 over 13 times 3 plus b. If you bring everything to the left side, 1 is 13 over 13 plus 27 over 13, which will give you 40 over 13, and that's your b value. So the final answer for the equation of the tangent line on that infinity symbol at 3, 1 will be, poof, minus 9 over 13x plus 40 over 13. And what I did for you, I took the time to go back on the infinity symbol at the point 3, 1, and I drew the equation minus 9 over 13x plus 40 over 13. And that equation is, of course, tangent at that point. So we can see that these ideas can be used to construct the equation of the tangent line at any point on the curve where there is a derivative. So you need to make sure before you do all that stuff. Okay, so if we are interested to compute dy dx at a specific point to get the equation of a tangent line, we need to make sure that there is a tangent line. So when you have a curve in front of you, you should know first where you cannot do this. And then for any other point, the formula that we constructed for dy dx will be an equation that will compute the slope of your tangent line. And if you have a starting point, you can also now construct the equation of the tangent line so you can figure out what b is. All right, for that beautiful example, that's it. That's all. Let's do another example. Let's find the equation of the tangent line of the cardioid at the point 0, 1/2. And also let's identify on the curve the points where the implicit differentiation cannot exist, so where it does not exist, where there's no derivative. Actually, let's do that part first. Let's go on the graph and let's find those points on the curve where there's no derivative. So here, if I go on the graph, so here, this equation, the corresponding graph, which will always be given if we're asking you those visual questions. So here we have this, the reason why it's called a cardioid, it looks like a heart. So here there's 4 points where there's no derivative. There's the corner at the origin at 0, 0, and there's actually 3 points where the tangent line would be a vertical line. So here we go. So we have all those points. So I've put in red the corner, my vertical tangent are in magenta. So at those 4 points, there is no dy dx. Okay, so you cannot compute the derivative using the implicit differentiation tricks. Okay, so those points are out of question, but we want the point 1/2, 0, 1/2. So we will be able to do that. We can kind of see already that it is possible to compute the slope of the derivative there. So let's now do it. So for you, I've already written down all the details. So one thing here in this question that makes this question a bit more annoying is that on the right side, you need to square it. If you do the detail, you can actually simplify this equation to y squared is equal to 4x4 plus 8x squared y squared minus 4x cubed minus 4x y squared plus 4y to the power 4. So typically in the question, you don't need to worry. If there's a way to simplify it, it's already going to be done for you. We don't want to waste any time, okay, doing algebra. So what's really important here is that we want to differentiate that equation. So the first thing you do, so we have an equation with 2 sides. You compute the derivative on both sides. You just put d dx on the left and on the right. This will show clearly that you know you need to compute the derivative on both sides. And now you do it. The next line is the most important line. So the next line is what? So derivative of y squared is 2y times dy dx because it's a y term. The derivative of 4x4 is going to be 16x cubed. That's regular stuff. Be careful. 8x squared times y squared, that's a product. So you need to use a product rule. So if you differentiate 8x squared first, you get 16x times y squared plus, using my product rule still, 8x squared times derivative of y squared, which is 2y dy dx. So we're done with the product rule. Minus derivative of 4x cubed is going to be 12x squared, so minus 12x squared. Now for the other term, so we have minus 4x times y squared, so another product rule here. So we're going to get the derivative of minus 4x, which is minus 4 times y squared, plus minus 4x times the derivative of y squared, which is 2y dy dx. And then for the last term, the derivative of 4y to the power 4 is going to be 16y to the power 3 times dy dx. So just be careful. term by term. A term that purely depends on x, you just do the regular stuff. A term that purely depends on y, you do the regular stuff times dy dx. If the variables x and y are multiplied, if it's a product, you still have to do the product rule. So just be careful and you're going to be able to do it correctly. Now at that point, you just label where are the terms that depends on dy dx. So just to be annoying here, I've decided to bring all the dy dx term on the left side. So here on the left side, I get 2y dy dx, which was already on the left side, minus 8x squared 2y dy dx, that came from the right, plus 4x 2y dy dx, that came from the right, minus 16y cubed dy dx, that also came from the right. And then on the right side, I just have all the terms that does not depend on dy dx. So I have 16x cubed, I have 16xy squared, minus 12x squared, and minus 4y squared. Now on the left, I only have terms that are having a dy dx in common. So I just factor by dy dx, and then I divide. So here I'm going to skip it. I'm not going to read it for you. So it's just the regular stuff. So factor, my common factor is dy dx. The goal is to isolate dy dx. So you factor dy dx, and then you divide. So your final answer, dy dx, the implicit derivative is 16x cubed plus 16xy squared minus 12x squared minus 4y squared, all that over 2y minus 16x squared y plus 8xy minus 16y cubed. This is the last algebraic step. So now we have a formula for the derivative. That formula works for all the points on the cardioid except those 4 bad points that we've labeled earlier. But because we're doing this at 0, 1/2, it's one of the good points where we can compute the slope of the tangent line and where we can compute the equation of the tangent line. So here, simply by replacing every single x by 0 and every single y by 1/2, I'm going to get my m, my slope. If you do this, you can verify that this one simplifies very nicely to 1. So we know at this point that the equation of the tangent line is going to be of the form 1x plus b, and we know it's passing through or going through the point 0, 1/2. So if you replace x by 0 and y by 1/2, of course, the b is going to be equal to 1/2. So this means, in conclusion, that the equation of the tangent line on the cardioid at the point 0, 1/2 is given by x plus 0.5. And if you draw it here in orange, you can see that it's doing a perfect job here. That line x plus 0.5 is tangent to the cardioid. It's spanking the cardioid at the point 0.5 perfectly. This is doing exactly what it's supposed to do. All right. For that introduction of implicit differentiation and how you can use it to compute the equation of the tangent line almost everywhere on your curve. That's it. That's all. Bye-bye.